This is section 2.2a, polynomial functions of higher degree. And before we get into the slides, we should clarify what we mean by degree, just in case you forgot. You might have seen it in Algebra 2. When you're talking about a polynomial, degree is the number of the highest exponent. Alright, so with quadratic functions, which are in the form of ax squared plus bx plus c, the highest exponent is 2, and so quadratic functions have a degree of 2. Cubic functions, they have a degree of 3 because the highest exponent is 3, and so on. Okay, so that's what we mean by degree. Degree simply refers to the number of the highest exponent. Polynomial graphs are continuous. This is one thing that you need to keep in mind about the graphs of polynomial functions. They have continuous graphs. There's no interruption in them, no discontinuity. Notice that this graph on the right is discontinuous, so it can't be a polynomial. Polynomial graphs also have smooth turns. You never have sharp turns in a polynomial graph. Okay, and therefore if you ever see a graph such as this function, f of x equals absolute value of x, a graph like that with a sharp turn is not a polynomial. It simply doesn't qualify as a polynomial. Now we're going to talk a little bit about monomial graphs. Okay, if polynomial means that there are several terms, well, monomial means there's only one term. So let's just take a look at some monomial graphs because they're going to help us understand polynomials. Here are some monomials, and you see that the g of x here is x to the 4th power, and f of x here is x to the 2 power, and of course x to the 2 power is, or the 2nd power is simply read x squared. But these are both monomials. You can also think of them as parent functions. X squared is the parent quadratic function because all other quadratic functions are based on it. They derive from it. And x to the 4th is the parent quartic function because all quartic polynomials are based on x to the 4th. So you can think of these as parent functions if you like. In any case, these are also monomials, and x to the 4th would be a monomial of degree 4, and x squared is a monomial of degree 2. Let's look at the way these graphs behave. Well, notice that the exponents here are even numbers. 4 is an even number, 2 is an even number. And notice how the graphs behave. In both cases, when we're dealing with these negative x-coordinates, as the negative x-coordinates get bigger, the value of the function gets bigger. And as the positive x-coordinates get bigger, the value of the function gets bigger. So we would say that these graphs, they rise to the left and they rise to the right. And by rise, we just mean, of course, that the graph goes upward. All right, so they rise to the left and they rise to the right. What's another thing that we can see about these graphs? Well, let's look at the x squared graph. We have that nice, parabolic shape. Remember parabolas from chapter 10. Well, we have that nice parabola, f of x equals x squared. But x to the 4th, although it does look somewhat similar, we notice two differences. One difference is that in this portion here, when the x-coordinates are, between 0 and 1, or between 0 and negative 1, well, the values of the function are smaller. But then for the portion of x-coordinates that are greater than 1 or x-coordinates that are less than negative 1, we see that the values of the function are higher. And so we have a steeper graph here. And then in the other portion we have graphs that are kind of flattened out around the vertex area. Well, that's just because of the nature of fractions. 1/2 squared is 1/4. But 1/2 cubed is 1/8. If you raise fractions to high exponents, you get smaller and smaller numbers. So that explains why in the x to the 4th power graph here, I'm getting smaller values because the x-coordinates are fractional. However, for x coordinates greater than 1, we're not dealing with fractions anymore. We're dealing with whole numbers, or even whole numbers plus fractions, but that's still bigger than a fraction. And when you raise those numbers to exponents, you get bigger and bigger numbers. And that explains why in the portion of the graph where the x-coordinates are greater than 1, for the x to the fourth graph, I have higher and higher values. Now, some of this might seem pretty obvious to you, but the reason we're going through it is because in this chapter, we're really learning how functions behave. And so it helps to become familiar with these shapes and also familiar with the behavior of these functions' graphs. Let's look at these examples. F of x equals x cubed, g of x equals x to the fifth. The x to the fifth graph is this graph in black, and the graph that's in gray is my x cubed function. Notice that the behavior is similar in some ways, different in others. Different because for both of these graphs, they fall left and rise right. And that's because the exponents are odd. For example, if you take -1 and you cube it, well, you get -1. Take -2 and you cube it, you get -8. So you can see that for negative x coordinates, the value of the function will be negative. However, for positive x coordinates, the value of the function will be positive. Cube 1 and you get 1. Cube 2 and you get 8. So that's how they behave when the degree is odd. Okay, so x to the fifth has a degree of 5, x to the third, x cubed, has a degree of 3. When the degree is odd, the graphs fall left and rise right. All right, let's see how the behavior here is similar to what we saw on the left-hand side of the screen. Well, notice that the graph of x to the fifth is quite steep once the x values are greater than 1, but it flattens out when the x values are between 0 and 1 because, we're raising fractions to exponents, and so we get smaller numbers than we otherwise would. All right, so again, these monomials just show us how the parent functions behave, and that will help us understand what we're going to get into next, which is how polynomials, or the child functions, if you like, the functions that come from these parents, how they behave. Just a little drill on monomials to see if you remember some things that we've done before. How would you sketch this? Okay, now you know that the graph of the parent x to the fourth would be the parent of this function. You know what its graph looks like from your notes from the previous screen. And so all you have to do now is adjust that, and you should recognize what kind of shifts we have going on here. So pause the video, sketch, and then resume when you have your graph. You should have sketched this, and as you can see, this is exactly like the parent x to the fourth function's graph, but it has been shifted to the left 1 unit and down 1 unit. Sketch negative x to the fifth plus 2. You'll recognize that the parent of this function is x to the fifth. So using the same process, pause the video, sketch a graph, and then resume when you have an answer. So you should have come up with this. The negative in front of the x-fifth, that gives us the reflection, and the reflection about the x-axis. And then we simply shift it upward 2 units. And you can see that's exactly what we have going on here. Behavior of leading coefficients. All right, so this will indicate the way that leading coefficients affect the behavior of graphs for polynomials. So if the function's degree n is odd and a is greater than 0, then the graph falls left and rises right. Recall that a is simply the leading coefficient. So that would be the coefficient in front of the variable that's raised to your highest power. So in the function 5x to the fourth minus x cubed, degree is 4, leading coefficient is 5. Right, that's all a is. A is simply your leading coefficient. And all this says is that if a is positive, that is, if a is greater than 0, then the graph falls left and rises right. All right, now refer to the notes from previous screen, and let's confirm that. Notice that for the function x cubed, right? That was on a previous screen. You should have already written down that graph because, as I've said before in class, everything on the screens is to be written down. Absolutely everything. All right, so refer to that graph of x cubed. And you'll see that, all right, x cubed, its degree is odd because the degree is 3. 3 is an odd number. And sure enough, it falls left and rises right. If a is less than 0, then the graph rises left and falls right. Now we saw something like that in the last example where we had, negative x to the fifth plus 2. Well, we had a negative a. In that case, the a was negative 1, leading coefficient was negative 1. And the graph rises left and falls right. It does the opposite because it's been flipped by the negative sign of the leading coefficient. If the function's degree n is even and a is greater than 0, then the graph rises left and right. Okay, we saw that in the previous screen when we were looking at the monomials for x squared and x to the fourth. Those degrees were even, and a, in that case, the a was positive 1. And we saw that the graphs for both, they rose left and right. And that's how functions graphs behave when a is greater than 0 and n is even. If a is less than 0 when n is even, then the graph falls left and right. That's simply because it's been flipped over by that negative sign. The negative sign in front of that leading coefficient makes something point downward. We saw that with parabolas because it flips it over. Now we'll see some examples of this in just a bit. For now, it's important to write this down because even though some of it might be common sense for you, for now you should write it down because you can quickly refer to it when you need to. Now, when we talk about falling left and rising right, that's kind of a way to describe it in English. But how would we write that in math? Well, that's what I want to go into next. If we translate the words falls left into math, all right, then falls left means that as x approaches negative infinity, then f of x approaches negative infinity. All right, think about that for a second. As I plug in bigger and bigger negative values as my x-coordinate, well then my y-coordinate, or my f of x, is going to be bigger and bigger negative value. That's all we mean by fall left. That's all we mean by fall left. All right, think about the x cubed function. If you have negative 1,000 cubed, you're going to get a very large negative number. If you have negative million cubed, you're going to get a very large negative number. Okay, that's all that we mean by fall left. As x approaches negative infinity, f of x approaches negative infinity. Rises left means that as x approaches negative infinity, f of x approaches infinity. We saw that with the x squared function, right? Plug in very large negative values into the x squared function and you get very large positive values. Falls right means that as x approaches infinity, f of x approaches negative infinity. Okay, so we saw that with the inverted cubic function, or the inverted quintic function, the degree of 5. It just means that if you plug in large positive values into the function, you're going to get bigger and bigger negative values. That's falling right. And finally, rising right means that as x approaches infinity, f of x approaches infinity. And of course, we see that, for example, in the quadratic functions. Plug in big values for your x-coordinate, and you'll get very big values for your y-coordinate, but it's still always going to be positive. Okay, so that's what rising right means. What we're doing so far is very qualitative. Qualitative just describes shapes and general trends. It doesn't really get into specific numbers. But understanding the qualitative is definitely the first step before you can understand and work with the quantitative. Examples describe the right hand and left hand behavior of the following functions. All we mean by that is, does it fall left, rise right? Does it rise left, fall right? Does it rise left and right, etc.? That's all we mean by describe the right hand and left hand behavior of the following functions. So describe the right hand and left hand behavior of 2x to the fifth minus 3x to the fourth plus x. You don't need to sketch this graph, but what I'd like you to do is pause the video, figure out what its behavior is based on the notes of the last screen. And when you have something written down, resume the video. Alright, well, this is the graph that of course you didn't have to sketch, but I'm putting it here just for your reference. You should have said that it falls left and rises right. Falls left and rises right. And that's because the A, in this case my A is positive 2. Since that A is greater than 0, and also since the degree here is odd, the behavior is fall left and rise right, just as the table on the previous page says. Now, the table on the previous page really is common sense, and it works when you just plug in numbers, and you can even prove it all to yourself. There's no need to prove what's on the table of the previous page. But it's good to have the table written because it's a quick reference guide. How about f of x equals negative 5x to the fourth plus x cubed plus 6? I want you to describe the right-hand and left-hand behavior of that function. Pause the video, resume when you have an answer. Alright, so you should have come up with this. Since my degree is even, my degree is 4 is an even number, and since my a is less than 0, since it's negative 5, then it falls left and right. Falls left, falls right. And we can see, of course, that the graph here falls left and falls right. Classwork, page 148. Please write these numbers down, and we'll see you in class.